Hi, my name is Savin Goyal. I'm an engineer on the machine learning infrastructure team at Netflix. And today I'm here to talk about some of the work that my team has been doing in the area of building a machine learning platform that essentially allows our data scientists to focus their activities and energy on data science and less on engineering concerns. Thanks for joining me. Let's get started. So for most of you, or for many of you watching this talk, when you think about machine learning and Netflix, the very first idea that might pop in your head would be our eponymous recommendation systems. So whenever you log into netflix.com on your television or your mobile device, you're presented with this UI where every single element of this UI, whether it's the rows, the actual content of the rows, or even the album artwork, every single aspect is personalized to your taste and preferences. Now, yes, recommendation systems happen to be our crown jewel. Netflix has been leading the charge in this area for well over a decade now. But now, as the scope of Netflix's business has grown over the last few years, the areas where we invest in machine learning has also increased quite a bit. As one of the biggest studios around, we place a lot of emphasis in terms of predicting how much viewership any given piece of IP will get so that we can very accurately identify a dollar value associated with any given piece of content. As one of the biggest subscription services, we are constantly fighting fraud, constantly trying to figure out what are some of the more efficient ways of payment processing. We also have significant efforts in terms of generating machine-generated subtitles for our TV shows and movies. We do a lot of automated screenplay analysis using NLP as one of the companies which has a huge footprint on the public cloud. We also have a lot of emphasis on machine learning based research around how to be a bit more efficient in terms of how we are utilizing our infrastructure in general. And as you can see, the diversity, we have a huge diverse set of use cases that people inside of Netflix are tackling on a day-to-day basis. And that inherently means that the kind of talent that Netflix hires for also comes from a diverse set of backgrounds. So, these are academic backgrounds ranging from computer science, physics, economics, public policy, and people bringing in diverse set of tooling along with themselves. We have people who are very much in the Pythonic universe. We have quite a number of individuals who would like to get their work done in R. We have individuals who are playing around with Julia. And that's where my team steps in. So my team's responsibility is to make sure that our data scientists, they have a very easy and convenient time moving their ideas from prototype to production in a manner such that we are not encumbering on their freedom of choice, on their freedom of tooling that they want to exercise. Let's talk about how we actually go about doing that a bit. And before I get into the specifics, let's talk about what does a data science stack look like at the end of the day. At the very low level of that data science stack, you sort of like start out with some sort of data warehouse, and that's essentially a euphemism for a place where you have your data. It could be a local file system where you have a bunch of CSV files lying around, or it could be a multi-petabyte data store on the cloud, say, on top of HDFS, on top of Amazon's S3, Google's GCS, Microsoft's Azure Blob Store. Along with a data warehouse for machine learning applications, you need some amount of compute resources. This can be as simple as your laptop or your workstation, or some sort of, let's say, a Kubernetes cluster where a user can essentially launch a job and specify some sort of resources, often in terms of the amount of GPUs, CPUs, memory, the space that they might need to sort of like train their model at the end of the day. They also need some way of scheduling these jobs. If you look at machine learning code, all of these training pipelines, ultimately there are some sort of a workflow at the end of the day where you might have a job which is prepping your data, then you might have a job which is training your model, yet another job which is figuring out, if the model that you just trained actually makes sense to be deployed to production. So you need some way of orchestrating these jobs one after the other. And on top of that, the user has to figure out how do they actually need to write their code so that they can very easily interface with these job schedulers or these job orchestrators and actually launch their jobs on these compute resources and interface with the data warehouse. Now, all of us in the room, we are very well familiar, right? Like machine learning is a very iterative process. You try out one idea, it may work, it might not work. Then you try out yet another idea, often with different hyperparameters. So there is this notion of quick iteration. So what that means at the end of the day is you have multiple different versions of your machine learning workflow that are executing at any given point in time, or any given duration of time. And that means that there is a strict requirement for some sort of experimentation management. It can be as simple as, using a notebook where you are sort of like scribbling down the result of a bunch of your experiments. And it could be as complicated as using some sort of version control system so that you have a good sense of the data that you operated on, as well as the code that executed and the results that you obtained. Now, as we move higher up the stack, we sort of like now start getting into the world of machine learning. It's almost funny. We talk about this data science stack, but then most of the things, at least at the lower levels of the stack, are concerns around systems engineering. So now at the upper levels of the stack, the data scientists, now they need to concern themselves with like, okay, how are they generating these features? How can they efficiently manage these features? Maybe they want to use a feature store of sorts, some sort of like catalog at the end of the day. And at the very top is the actual model development paradigm. What sort of IDE would your data scientists want to use? Do they want to use TensorFlow or PyTorch, or do they want to roll their own implementation of the algorithm? That's sort of like the deep stack of data science. So, at the top end, you have things that the data scientists care about the most, where they want to exercise their freedom. And at the bottom layer of the stack is where most of the heavy duty engineering work is required. And during our conversations with our data scientists internally, that's what we essentially observed as well. Our data scientists, they very much want to be in control of the actual machine learning libraries, the actual tool sets they get to use, but they don't necessarily have any express opinions whether the data is stored in S3 or it's stored in HDFS, as long as they get quick and efficient access to it. Yet again, as far as compute resources go, what the data scientists actually want at the end of the day is quick and efficient access to compute resources. If they want to execute some part of their workflow on a GPU, then they just care about having a way to access that compute resource, whether it's coming through a Kubernetes cluster or a Docker Swarm cluster, or some machines hidden in some closet somewhere. That's not really sort of like top of mind for them. From an engineering standpoint, from an infrastructure standpoint, the concerns are definitely bottom heavy. As infrastructure engineers, we very much recognize, like setting up these data warehouses, figuring out how to lay out the data in these warehouses, setting up query engines, creating and operating these Kubernetes clusters. These are heavy duty engineering tasks, right? Which requires a lot of effort, ongoing effort at the end of the day. And our goal was essentially to sort of like build a platform, build a framework, which allows data scientists to exercise their freedom at the top end of the stack, while we can take care of some of the opinions around the lower levels of the stack. And that is essentially what Metaflow is. So Metaflow is a highly opinionated framework that enforces most of its opinions and best practices on the lower levels of the stack, and frees up the user to express their opinions at the higher level. Let me talk about some of the user-facing concepts that we introduced in Metaflow. Predominantly through the course of this talk, I'll focus on three big pillars. The first one being usability. We want to make sure that as we introduce a new framework, we're not adding to the cognitive overhead that our users face. We want to make sure that any new library, any new tooling that we are using, ultimately at the end of the day, it makes our data scientist's life a tad bit easier. We also want to make sure that some of the primitives that we are introducing, they allow our users to scale out their compute really well. And what I exactly mean by that would be a lot more clearer as we go through this talk. The third major pillar is around reproducibility, and it's very closely tied to the notion of collaboration as well. Because if let's say I, as a data scientist, work on a certain problem, if my peers are able to reproduce the results that I had very reliably, then they can very easily build on top of those results, and that almost always aids in collaboration. So when we look at any sort of machine learning workflow, right? Say you have a piece of code that is training a model. Ultimately, at the end of the day, you have some sort of input, which can be a data frame. You perform some compute, which is essentially training your model on that input data set. And then your output is essentially the trained model, right? And that sort of like serves as a good baseline example for us. Now, these machine learning workflows, they can often be thought about as a directed acyclic graph. I hope that's not too controversial. For example, in this case, you have the start step where, you might be fetching your data from some data warehouse. You might be doing some data cleaning, generating some features. And then you might have these two steps, A and B, which depend on the output of the start step. And these two steps might be just training a model independently. And then in the joint step, maybe, you're comparing these two models against one another, trying to figure out which one is the better performing model. And then in the very last step, you might be storing that model somewhere for subsequent use. Now, Metaflow introduces this notion of decorators that sort of like allows our end users to very easily declare this graph. As you can see on the right side, we have this decorator at step. So our users, they will essentially implement this class flowspec. And as part of that, they will implement some of these functions. So you have the start method, method A, method B, method join, and they'll just drop in these decorators at step that will sort of like inform Metaflow that each of these methods are essentially nodes of this graph. And then we also have the self.next method that will delineate what are the transitions between these different steps. So for example, in the step start, we declare that after the step start is done, we need to transition into step A and step B. And then both step A and step B using self.next, they pipe into the step join. And then the step join, it pipes into step N. And now when the user executes this code, Metaflow takes care of the execution, and then it will automatically parallelize the execution of step A and B. And that's incredibly helpful for our users when they have to sort of like think about how to structure or architect their code in a very reasonable manner. Now, this notion of a DAG-based workflow, it's not new. There are like plenty of frameworks that exist that introduce this notion for workflow execution. What Metaflow does is it also handles state transfer and persistence. So for example, say, you have some user code, you have some instance variable, let's say in this example, we have the variable x, and you might define the variable of the value of x as say 0 in the start step. And then if you're writing idiomatic Python code, then the expectation would be that that value of x is available to you in all of these other methods as well. And you can very simply do that with Metaflow as well. And in that way, the user ultimately at the end of the day, they are writing very idiomatic Python code that they are very well familiar with. Now, this example is rather interesting because now when the step A and B, both of them execute, now you have two different value of x's. And then Metaflow will take care of making sure that the join step essentially gets a list of x values, so 2 and 3 in this case, and then the user can then figure out what to do with that. So like x can also be a model. So step A might train a model, step B might train a model, and now the join step will have access to both the models, and then the user can figure out how to better use that. Now, one interesting artifact of sort of like organizing your code in this manner is that now we can be super fancy in terms of the execution environment that we provide for every single step. So, let's, for example, take a hypothetical case where step A, it needs to train a model on a bunch of GPUs. And maybe, your laptop doesn't really have those GPUs. So now how do you do that? Or maybe, your step start, it needs to process a huge data frame and you don't have sufficient memory in your laptop. How would you go about doing that? Now, one way of thinking about such data processing is to, like think about like the MapReduce paradigm or some sort of like distributed computing paradigm. But what's interesting to note here is that, over the last 15 years or so, the amount of resources that are available in one single instance has continuously increased. When the MapReduce paper came out, a general purpose instance in the AWS cloud had roughly 1.6 gigs of memory available. So at that point in time, a lot of problems, you just could not solve those problems in one single instance. And that's what like necessitated a MapReduce based approach. But now, you can log into your AWS console and you have access to, machines which have like terabytes of memory in them, which means that now increasingly there is an increasing set of problems that can be executed on one single machine. And that's sort of like the philosophy that we advocate to our users as well, that if they can somehow execute their code on an instance with much higher resources, then that's always a better strategy than sort of like re-architecting their code and making sure that, it works in a distributed manner. So as part of that, we have this add resources decorator where our users can very simply specify what are the resources for any given step. And then Metaflow will take care of sort of like farming out the compute for that particular step onto a remote instance with those many resources. So for example, in your step A, you might want to execute that on an instance with 16 CPU cores, your step B with 200 gigs of RAM. And Metaflow will then automatically take care of executing the user code on these remote instances with the specified resources. But then again, there might be times where, you might just want many different machines together. Scaling up might not really solve your use case. In machine learning world, there are many instances where you want to train many different models on a set of hyperparameters. And in Metaflow, we have introduced this feature, this primitive for each, that allows you to essentially iterate over a list. So in this example, we have self.grid, which has 3 items, X, Y, and Z. And when you execute your code with Metaflow, it will automatically launch the user code in step A on 3 different instances, each of them with 200 gigs of memory. And that allows our users to very efficiently farm out compute. Yet another issue that a lot of people run into is how to manage dependencies. If let's say we take this very hypothetical example where you might want to train 2 different models using 2 different libraries, say TensorFlow and PyTorch, how do I actually create this encapsulated environment in a very easy manner without actually having to worry about, like what is Docker and like how do I sort of like get these dependencies and how do I install these? So Metaflow integrates very deeply with Conda, which is an excellent package manager for the data science community. And what Metaflow will do is for each of these steps, it will create an isolated environment with only the dependencies that the user has specified. And it will also cache these dependencies in the backing data store so that we can very reliably regenerate, rehydrate this environment at any time in the future. And that's incredibly powerful because now our users, they're not tied to any of the infrastructural offerings in terms of, hey, you can only use this version of TensorFlow or you cannot use PyTorch and so on and so forth. And that's incredibly powerful in terms of making sure that our users can, at the end of the day, exercise their freedom of choice. It also, Metaflow takes care of reproducibility. So every single execution is versioned. So we snapshot the user code, we snapshot all the internal state as well as the environment. And using a client that we provide, people can actually inspect the code that was executed, the data that was processed, as well as the environment in which the code was executed. And that really helps in verifying prior executions as well as aids in repeatability of the machine learning workflow. The other aspect of providing such a client utility is for a very long period of time, we thought very deeply about like, okay, what sort of UI should we provide with Metaflow for users to track their machine learning workflows? And we kind of like came to a conclusion that each of the machine learning applications, say, NLP to computer vision, are distinct enough that it's very hard to build one single UI that can satisfy all the use cases. And we essentially took the approach where we provide these primitives where our users who are already familiar with the notebook ecosystem, they can very easily create these custom dashboards. So for example, in this case, the user might want to track whether my step A of my flow latest execution has succeeded or not. And if it has succeeded, I might just want to print the value of X that was set after my step A completed. Or if it failed, then I might just want to print the error logs. And our users can then now very simply create these very complicated dashboards, which completely suit their purpose in a very self-serve manner. Yet another interesting artifact of machine learning workflows is what do you actually do with the model, right? You have spent so much time training your model, but then if you cannot reliably use it, then what's the point of even training a model in the first place? And Metaflow supports multiple different ways of exploring your model in a production setting. You might want to export your model and do batch inferencing, or you might want to host your model as a REST API. And we provide a function as a service platform where the users ultimately are writing these Pythonic functions, and then Metaflow will take care of hosting these as microservices or as batch processes, so that now the model that was generated can actually be integrated into a production service. Yet another notion of production for machine learning workflows is around, now I have my workflow, my model training workflow running reliably on my laptop with, either some or all of the steps running remotely. But now I want to schedule it. I want to make sure that, it executes in a very reliable manner when, let's say, there's a new data partition, or say, at the stroke of midnight every single day. And I want to make sure that, if my workflows fail, then I'm suitably alerted, and I want all the bells and whistles of production grade workflow executors. And now the good thing is that Metaflow is executing a DAG, and most of production workflow schedulers, say, AWS step functions or Airflow, they also execute DAGs at the end of the day. And what Metaflow allows for is it will automatically compile the user code, the user workflow, into a format that is understood easily by these production workflow schedulers. So now you can enjoy the best of both worlds. You can write your workflows without actually worrying about any of the concepts of these production workflows. And then when you are ready, at that point in time, at a click of a button, you can export these to a production workflow scheduler, and you sort of like get all the goodness around like high availability, resiliency, error messages, monitoring from any of these workflow schedulers. So sort of like the best of both worlds. Metaflow is also polyglot. So as I mentioned before, we have a significant number of users who work in the Pythonic universe. We also have a lot of users who are in the R universe as well. And we provide parity between all the functionality that Metaflow has, so that our R users can sort of like enjoy all the functionality as well. We are running almost out of time, but as I mentioned before, right, every single execution of your workflow is executed in a specific namespace, so that all executions are isolated, as well as we snapshot, we give it a unique ID. We snapshot all the internal data, and that allows people to sort of like look and explore other users' executions as well. And then they can very easily piece together super complicated workflow where my workflow might depend on some other user's workflow's execution results. So this was Metaflow. We focus on usability. We want to make sure that any of the functionality that we offer is fairly intuitive, so that it's not adding to the overhead of our data scientists, and it can aid in their productivity. We try to approach reproducibility by isolating every single execution, making sure that the environment is abstracted and snapshotted reliably. And for scalability concerns, we highly advocate users to think about vertical scalability before thinking about sharding their workflows in a horizontal manner. So that's Metaflow. That's the work that my team has been involved in over the last couple of years. Metaflow is also an open source project, so all the features that I spoke to you about, they are available to you. Please visit our website at metaflow.org. And if you have any questions, I would be happy to take those. Thank you.